And in the beginning was the first Calc 1 exam, and there were 7 problems, and it was good. So let's go through and do this exam. The Calc 1, also known as Math 165, first exam from fall 2023. We're going to have a lot of fun. As always, start by putting our name down, because if we don't put down our name, we won't get credit, and we like credit. All right, let's begin. Number 1, let f of x be the function ax cubed plus bx to 3 halves minus 4. And we're asked, find a and b. So there's these two constants. We're going to figure it out so that both of these statements are true. The first thing is that the average rate of change of f of x between 0 and 1 is 9. And the second, instantaneous rate of change of f of x at 4 is negative 18. All right, so this problem is sort of testing us rates of change. We have average rate of change, instantaneous rate of change. We want to make sure we understand both of them. So let's start with the first bullet, which is the average rate of change. Okay, well, how does one figure out the average rate of change? Well, the way the average rate of change works is it says, well, it would have to be the rate of change as a constant if I want to achieve the same result. So in other words, the function may do wild things, but it's like, okay, imagine it were a line. What's the slope of the line? Because slope is like a rate of change. So how do you figure it out? Well, you say your average rate of change is as follows. It's f at the endpoint, which we usually use a's and b's, but little a's, little b's, minus f at the beginning over b minus a. So if it looks like the slope formula, it's because it is a slope formula. So if nothing else, the average rate of change thinks slope formula. Start and stop. Now in our case, we know where we're going between. So we're starting at a equals 0, ending at b equals 1. Now if you swap a and b, don't worry, the sign works itself out. So this would be f of 1, subtract f of 0, divide by 1 minus 0. Oh, two of our favorite numbers, 0 and 1. They make it very easy to compute things. We're dividing by 1. That doesn't do anything. So say, okay, plug in 1. Well, what do you get when you plug in 1? Well, you get the following. A times 1 cubed, which is A. B, 1 to 3 halves. Well, 1 to 3 halves is 1, so we get B. And then we have minus 4. But don't forget, we also have to subtract. Well, plug in 0. A times 0, 0. 0 to 3 halves, 0. Minus 4, minus 4. Okay, so 0 plus 0 minus 4. Notice the minus 4s will cancel. So woohoo, nice. So we're left with A plus B. And remember, we know what the average rate of change is. It's 9. So A plus B must equal 9. Okay, so this gives us a relationship between A and B. So we've made progress. We're not done, but progress has been made. And that's always nice when you make some progress. So now we get to our second thing, instantaneous rate of change. Now, if you see the word instantaneous rate of change, that's derivative. So derivative is what's happening at that one moment in time. So we say, okay, instantaneous rate of change. I guess normally people don't abbreviate this way, but I'll do that just so. All right, I for instantaneous. That's our f prime at our point. Okay, so, well, we need to know the derivative. So let's do our derivative. Okay, we'll do a little bit of side work here. F of x would be, just copy it down. We don't know what a and b are, but we can copy. We're good at that. Minus 4. Okay, f prime of x. Well, take the derivative, and we get 3a x squared, because remember the rule is power comes down, subtract 1. And then plus 3 halves b, power comes down, x, subtract 1 to the 1 half. The derivative of minus 4 is 0. Ah, lovely, lovely. Okay, so now we're going to plug in. Now, what are we plugging in? Well, we're at 4. So we're plugging 4 into here. So we want to look at f prime of 4. So that's going to be 3a times 4 squared plus 3 halves b times 4 to the 1 half. All right, well, 4 squared, and 16 years ago, oh wait, no, that's not that. 4 squared is 16. 3 times 16, whoa, big number, 48. 48a. 4 to the 1 half is 2. 2 times 3 halves is 3. So we get a 3b. And that's the instantaneous rate of change. And it equals negative 18. All right, equals negative 18. Remember, the word is means equals. All right, well, we can, oh, that's supposed to be a capital B, excuse me. We can divide by 3 in this equation here, because all of these are multiples of 3. So that tells us what? 16a plus b is negative 6. Okay, second equations. Now we have two equations. Two unknowns. Perfect. This is our favorite scenario. We love 2 equations, 2 unknowns. Or at the very least, we're going to get really good at solving them, because we're going to see them a lot throughout calculus. Okay, so here we go. Move this up ever so slightly. And so we have our a plus b equals 9. 16a plus b equals minus 6. And let's combine them. And notice they both have b's. So if we subtract one from the other, a subtract 16a gives us negative 15a. b subtract b equals 0. That's the idea of cancellation, right? Cancel something. 9 subtract negative 6. 9 plus 6. That's 15. So negative 15a equals 15. That says, oh, a should equal negative 1. Well, now that you know a equals negative 1, you can come back, plug it in, say to the first equation, negative 1 plus b, it should equal 9. So what's b? Well, add 1. That tells us b equals 10. Good. And remember, what were we looking for? We were looking for find a and b. Well, we found a. We found b. That's everything we were asked to find. And so we can put it all together so that our grader can easily find the answer. And of course, when graders can easily find the answer, they like us more. Put it in a nice little box. Beautiful. And we're good to go. Now, on a side comment, before we leave this one, you may say, this negative 4 didn't seem to really do anything. Is that a mistake? Or is that something that should happen? Well, the thing is, what is the negative 4 doing? If we think about this function, you can think of negative 4 as being a vertical shift. So it's like you're taking the graph and you're moving it, in this case, down by 4. Now, if you move the whole thing down by 4, how does that affect your rates of change? The answer is, it doesn't. It changes the graph, but it doesn't change the rates, because rates are relative. So if you shift everything, lines shift down. So the tangent line shifts down, the line between the two dots that makes average rate of change shifts down. So this negative 4 is meant to be a little bit distracting. So, all right, well, there we go. 1 down. Woohoo! Number 2. Compute the following derivatives. Do not simplify. Look at that. It's like they're like, no, don't do it. Don't simplify. Mostly because it's hard to check once you simplify. But there's other things that happen when you simplify. Sometimes you make mistakes in the simplification. But another thing that happens is when you don't simplify, we can really get a sense of like, all right, what did you do? And where were your mistakes? Now let's see what we have here. In the first problem, what do we have? We have upstairs, square root of x, downstairs, pi plus sine x. It's a function over a function. What rule do we need? Quotient rule. Quotient means division. All right, so quotient rule. Oh, now this is the one that can be a little bit tricky. So we just have to remember our rules. So we have the derivative of our function, square root of x, over pi plus sine x, is you take the bottom function, so we'll do this in 2 steps, bottom times the derivative of the top minus the top times the derivative of the bottom, and then after all of that you divide by the bottom term squared. All right, so that's what will happen. Now this is not the answer because we still have to finish taking derivatives. Okay, now before we do that, I just want to make a quick side note. Square root of x as the notation, square root of x, we oftentimes get that in algebra, but it's not the best way to use it in calculus. So calculus, we like our rules, and so instead of thinking this as square root of x, we should think this as x to the 1/2. Because our rules are like, how do you handle x to a power? So if we want to use our rules, we should make it look like our rules. So it should look like x to a power. All right, so here we go. We're ready. So we have our pi plus sine x. Derivative of square root of x, well, it's x to the 1/2. So 1/2 comes down. X 1/2 minus 1, negative 1/2. Now here we can leave this as square root of x. Why not? Now, the derivative of pi, 0. Pi is a constant. That's good. Derivative of sine of x. Well, derivative of sine is cosine. Now, of course, sine and cosine are a little bit interesting because, of course, one of them has a sign where, so be careful, be careful. And then downstairs, well, we don't need to do anything. It's already been done. Pi plus sine x, quantity squared. And we are done with part A. Nice, good. Quotient rule, quotient rule. Now, if you don't like quotient rule, there are other ways to do this. One thing you can do is you can say, well, you can think of square root of x over pi plus sine x as square root of x times pi plus sine x to the negative 1 power. And in this case, you would do a product rule mixed together with a chain rule. And so if you were to do it this way, it is a correct way to compute the derivative, and it should receive full points. But hopefully you can do both at this time, and both by saying both these ideas. Okay, on to part B. Well, we have x cubed times e raised to the power 2 tangent x. So this has a couple of fun rules involved. We have two functions multiplying. So two functions multiplying tells us product rule. We also have a function inside a function. Function inside a function tells us chain rule. And technically, we even have constant times a function. And constant times a function says, hey, just leave the constant alone. And so, all right. So lots of pieces putting it together. And so this often happens when you talk about derivatives. You have lots of moving parts, and then you just have to say, okay, how do things fit together? And I like to think of these as sort of onion problems. There's layers. And not only are there layers, maybe there's tears. Tears of joy at how happy we are that we get to do this problem. All right, so here we go. What's our outer layer? Well, our outmost part is a product. So we're going to start by doing a product rule. So we'll do this a little bit slowly just to emphasize. You don't have to go into quite as much detail as we'll go here, but it's good to really make sure we understand what's going on. So we have the derivative of the first times the second plus the first times the derivative of the second. And again, on these kinds of problems, oftentimes you can just write down the answer. I'm just doing it slowly just to emphasize the process. You know, what's going on up here? The derivative of x cubed, well, 3 comes down, 3x squared, and this other part we're leaving alone. And then we have our x cubed. Now, chain rule. Our inside function, that's easy to spot, 2 tangent x. What's our outside function? It's the exponential function. It's e to the power of something. Now, the good thing about the exponential function is it's really, really nice. Taking the derivative of the exponential function, it's the exponential function. It's why it's, you know, one of our top 2 or 3 favorite functions in calculus. It's just so resilient. And we say, okay, so what's going to happen? We take the derivative of the exponential function. We still have e. So we have e. We leave the inside alone. So this is sort of our f prime of g of x times that by the derivative of the inside, 2 tangent x. And so we have 3x squared e to the 2 tangent of x plus x cubed e 2 tangent of x. And the 2, because it's a constant, just comes along for the ride. The derivative of tangent secant squared. So add a secant squared, and then we say, look, we don't need to simplify. So we put it in a box. And we're done with part B. All right. Well, good. Know your derivative rules. Because if you don't, you're in trouble. I mean, I don't like to say that, but this is all derivatives. This class is all about derivatives. And the sooner you know the rules, the happier you'll be, and the more successful you'll be. So know your rules. Know your rules. Number 3. We're given that the position of a particle follows this curve, s of t. So s for position. Someone told me it comes from a German word, but okay, let's just go with it. And t we think of as time. 3/5 t to the 5th, 5/2 t to the 4th, minus 3t cubed. Okay, so a particle is moving. We're thinking of it really as moving in one direction, so it's a one-dimensional problem. Determine all. All right, so maybe there's more than one. Values of time t, t greater than or equal to 0, so that the acceleration of the particle is 0. Okay, so we're given position, that's what we were told, and we want to say something about acceleration. Well, what's the relationship between position and acceleration? Well, one thing is there's sort of an intermediate layer. So there's velocity. Velocity says, how is your position changing? Well, change means derivative. So velocity will be the derivative of position. So we have that v of t is s prime of t. Well, now why do we care about velocity? Well, acceleration is, how is your velocity changing? So we can say, well, acceleration of t is v prime of t. And it turns out this is equal to the second derivative of position. So we're starting with a function. We're going to take 2 derivatives, and once we have those, we'll have our acceleration. And then once we have our acceleration, we can proceed figuring out the answer. All right, so let's start by taking our first derivative. Okay, so derivative of 3/5 t to the 5th. The 5 comes down. 3/5 times 5 will be a 3. And then we subtract 1, so 3 t to the 4th. 5/2 t to the 4th. The 4 comes down. 5/2 times 4 is 20 over 2, which is 10. T, subtract 1 from the power, cubed. Next term, 3 comes down. Minus 3 times 3 is 9, so minus 9 t, and again, subtract 1 from the power, squared. All right, now another derivative, right? Because we're taking the derivative of velocity. Well, the 4 comes down, 12, and then subtract 1 from the power, t. cubed. The 3 comes down, 30. Then subtract 1, t squared. The 2 comes down, minus 18 t to the 1. All right, so now we have our acceleration function. And what do we want? Well, we want to know when is acceleration 0. And we really, the is 0 means equals 0, right? Because is means equals. Okay, wow, a cubic. Oh my gosh. Wow, but wait, it's not so bad. What can we do? Notice everything has a factor of t. Also, the coefficients, they all have factors of 6. So let's go ahead and factor out a 6t. And, well, what's left? We have ourselves t squared. Oops, sorry, 2t squared, because 12, when you pull out 6, is 2. 2t squared plus 5t, and, all right, 30 divided by 6 is 5, and then minus 3. Okay, so what can we do? Well, we have some choices. One thing is we can try to factor, or we can use quadratic formula. Which one is correct? They're both correct. Now, trying to factor will succeed if it's reasonable to factor. And this one is not, I think it'll work. But it can feel a little bit, just because you have numbers in front of here. Oftentimes we're so used to when we have like a 1t squared. So throwing in a 2 in front of our t squared. So how do we do this? Well, we don't panic because, of course, panicking, that's not us. We're calm. We're relaxed. We're going to succeed. So let's use a quadratic equation, quadratic formula, if you will. All right. So we say, okay, from here, what would we say? If I were solving for t, for roots, well, we'd get negative b plus or minus square root b squared. Well, okay, that's 25 minus 4ac. So 2, negative 3. And then divide that by 2a. So 2a would be 4. Okay, so that's negative 5 plus or minus square root. Well, minus minus makes a plus. 4 times 2 times 3 makes 24. 25 plus 24, 49. Aha! And does 49 have a nice square root? It does. Negative 5 plus or minus 7 over 4, which leads us to possibilities. Well, we have negative 5 plus 7 over 4, and negative 5 minus 7 over 4. Now, minus 5 minus 7 is minus 12. Divided by 4 is minus 3. Minus 5 plus 7 is 2. 2 over 4, a half. All right, so we have these two solutions. We have one more. Don't forget here. This would be t equals 0. So, what are our answers? Well, we have acceleration equals 0 when t is 0, a half, or negative 3. So is that our answer? Now, if you've hung around with me for a while, you'll be like, I don't know, Steve, very suspicious. Be careful. Read the problem carefully. Determine all values of t, and then there's this condition here. T must be greater than or equal to 0. Is negative 3 greater than or equal to 0? No. So this is not greater than or equal to 0. So it's not one of our solutions. So you want to make sure everything's satisfied. But both of these work. These are both greater than or equal to 0. So our final answer is 0, 1/2. And you might wonder, would they really take off a point if you included -3? Yeah, they probably would. They're like that sometimes, but that's okay. We still love our calculus teachers. They're good people. They love us. Number 4. Determine the value of a for the function f of x equals x squared plus a plus 7, such that the tangent line to x equals 4 is parallel to y equals 2x plus 1. Okay, interesting. Now, what do we see? Well, we see the words parallel. So let's start by decoding that. What does it mean for two lines to be parallel? Well, parallel is another fun way of saying same slope. Okay, great. So we just want to make sure our slopes agree. Well, let's look at the line. What's the slope of the line y equals 2x plus 1? So here, the slope is 2. All right. What about this tangent line? Well, how do you find the slope of a tangent line? That's actually a really important concept. What is the slope of the tangent line? The answer is it's the derivative. You see, the derivative is measuring, we've talked about it on an earlier problem, instantaneous rate of change. But what it's capturing is it says, oh, nearby your function, it kind of looks like a line. Well, what line is it? And the derivative is saying, hey, I can tell you the slope of that line. So we say, okay, so slope of the tangent will be what? Well, it's going to be f prime of 4, because we're at x equals 4. So now we see that part A is really saying, okay, find the value of A, so that we want to have f prime of 4 equals 2. Our tangent line at x equals 4 will have a slope of 2. So we have our function. Let's go ahead and compute that derivative. So the derivative of x squared, 2x. The derivative of a times x is a. The derivative of 7 goes away. So we need 2 times 4 plus a equals 2. So I'm plugging 4 in for x. 2 times 4 is 8. We can subtract. 2 subtract 8 is -6. And there we go. All right. Nice. Woohoo! Okay, so we got the answer. Now, part B. Find an equation of the tangent line to the function g of x equals sine of x at x equals 0. So it looks like part A and part B don't actually have much to do with each other than they're both testing on, do we understand tangent lines? Well, okay, so how do you go about finding tangent lines? Well, there's a nice formula for a tangent line, but essentially, if nothing else, just remember point and slope. Because what do you need to make a line? Point and slope. Well, how do we find the slope? Well, that was our discussion. The slope comes from the derivative. How do you find the point? You find it through the function. So, in particular, our point, well, that would be a g of a, where a is where we're at, and our slope, that is our g prime of a. So those are our two pieces of information. As long as you remember how to get point and slope, and you remember how to form a line from a point and a slope, you're going to get it. Now, I like this formula, namely which already gives it, and I'd like to write it as y is equal to g at the point plus g prime of a, x minus a. This makes it, this really sort of sets the groundwork for things which are to come. So let's look at our functions. We have g of x is sine of x. G prime of x, derivative of sine, positive cosine or negative cosine? It's positive cosine. Good, 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 good. Yes. All right. Now, we need g of 0 because we're at x equals 0. Sine of 0. What's sine of 0? 0. G prime of 0. Cosine of 0. What's cosine of 0? 1. If you're thinking in terms of the unit circle, an angle of 0 means you're right here. The x value is the cosine, so that's why cosine of 0 equals 1. The y value is the sine of 0 equals 0, because this is the point 1 comma 0. Okay, we plug it in. So we have, in particular, g of 0 plus g prime of 0 times x minus 0. Well, that's equal to 0 plus 1 times x minus 0. Normally you don't write this all out, but I'm doing that just to emphasize the process. Equals x. So the derivative of sine of x at x equals 0 is x. Another way to say that is near 0, the sine function looks a lot like y equals x. All right, well, that's nice to know. All right, good. Hey, we made it. We're over halfway. Woohoo! Number 5. Consider the function f of x equals e to the power 2x, subtract 5e to the x plus 6, divide that by e to the 2x minus 3e to the x minus 4. 2 parts. Part A. Find all the horizontal asymptotes of f of x. All right, so we're starting off with the horizontal asymptotes. Justify your answer using limits. Now, how does one find horizontal asymptotes? Well, horizontal asymptotes is as you head off towards the infinities. And there's 2 different infinities, right? So if we're going this way, well, that's towards positive infinity. And if we're going this way, that's towards minus infinity. That's why we can have 2 horizontal asymptotes. We can't have 3 because there's only 2 different infinities. And it's possible we have less than 2. So how do we figure out what's going on? Well, we have to see the different limits. So let's start towards the positive side. You know, we're optimistic. We want to be positive here. So we're going to take limit as x approaches positive infinity of f of x. All right, so that's e to the 2x minus 5e to the x plus 6. Divide that by e to the 2x minus 3e to the x minus 4. All right, well, what do we see? Well, now we just sort of start by reasoning what's going on. So before you do anything, ask yourself what's going on. We're plugging in big positive numbers. When you plug a big positive number into the exponential function, what do you get? A really big number. So we have big, huge number minus another big number plus 6. And huge number minus another big number, subtract 4. Okay, so it's right now huge number over huge number. It's not so clear what's going to happen. Well, actually, it kind of secretly is, right? We can kind of get an idea of what the answer is, and we know it pretty early because we say, well, which of these pieces is most important? In other words, which of them is the biggest of all these big parts? And the answer is the first part. So it looks a lot like e to the 2x over e to the 2x. So we think the answer should be 1. But we're still going to justify it because we like points. We want all our points. Okay, so how do we get to that point of justification? Well, what we're going to do is, since we say, things are getting big, we're going to slow it down. You know, there used to be in old cars, they'd say pump the brakes, which is another way, look, you need to get your car to slow down, so you want to slow it down. So we're going to slow it down just enough. So the way to do that is say, well, let's look at our biggest growth, divide out. So the thing that's growing the fastest is that e to the 2x. So what we're going to do is on both the top and the bottom, we're going to divide out by e to the 2x. And now that is going to slow things down. So we're going to positive infinity. E to the 2x divided by e to the 2x is 1. E to the x divided by e to the 2x. Well, you can think of that as e to the x over e to the 2x. Well, rules of exponents, you can subtract e to the x minus 2x. So that would become e to the minus x. And at the end, 1 over e to the 2x becomes e to the minus 2x. Now, downstairs, similar thing. E to the 2x over e to the 2x is 1. Minus 3e to the x over e to the 2x becomes minus 3e to the minus x. And then we have minus 4 over e to the 2x, e to the minus 2x. Now, what happens? Again, we stop and say, well, what's going on? And we say, well, as I plug in a big negative number, things get small. So this part, that goes to 0. 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 And now we're like, great, nothing's blowing up. So what we get is we get 1 minus 0 plus 0 over 1 minus 0 minus 0, also known as 1. Okay, so that's one of our limits. We're not quite done with it, but we're going to do our other limit, and then we'll put everything together. Okay, from the other side, negative infinity. So here we go. The limit as x goes to negative infinity. We have, again, the same function, so that we just copy down. Lots of writing here, but that happens a lot in math classes. You write down a lot. Now, again, plug in. What's going on? Well, when you plug in minus a big number into the exponential, you get a small thing. So the exponential is going to 0. Same thing with e to the minus 2x. So we say, oh, actually, we're pretty good here. We don't need to pump the brakes because nothing's blowing up. Everything's going to 0. So, well, not everything, not the end pieces. So what do we have? Well, upstairs we get 0 minus 0 plus 6, and downstairs 0 minus 0 minus 4, or 6 over negative 4, or negative 3 halves. All right, so as we head to positive infinity, we approach 1. As we head to negative infinity, we approach negative 3 halves. So what are the horizontal asymptotes? Well, horizontal asymptotes are flat lines. So they look like y equals something. So our horizontal asymptotes are y equals 1 and y equals negative 3 halves. And that's it. Those are our horizontal asymptotes. And we used limits, and so we have our justification. So we're good with part A. On to part B. Find all the vertical asymptotes. Okay, this is slightly different, of f of x, and then determine the one-sided limits of f of x from both sides of each vertical asymptote. Now, horizontal asymptote says as your inputs get large, what's going on? Vertical asymptotes are output gets large. Now, why might the output get large? Well, you might have a function like tangent, which blows up, but we don't. These are nice functions. And so what are we looking for? Well, the biggest culprit of vertical asymptotes, and like, I see you, divide by 0. So we suspect there's going to be a divide by 0 showing up. So, okay, great. Now that we know to look for divide by 0, well, how do we find it? So, well, that's going to be downstairs. But then you have, how do you handle an expression like e to the 2x minus 3e to the x minus 4? And we say, And as we say, we might have an idea. Or perhaps we've seen something like this before, which is to say e to the 2x. What's another way to think about e to the 2x? Well, another way to think about e to the 2x is that it's e to the x squared. Okay? So that's rules of exponents, right? Because e to the x to the 2, you multiply the 2 and the x together. Now you might say, well, how does that help us? Well, so let's look at our function f of x, and let's use this idea. Well, what we have is e to the x squared minus 5 e to the x plus 6, and downstairs e to the x squared minus 3 e to the x minus 4. Now, if you sort of squint your eyes, you'll say, oh, it looks like something squared minus 5 something plus 6 upstairs. Something squared minus 3 something minus 4 downstairs. In other words, they look like quadratics because they're quadratics. There's a reason they look that way. And, well, now that we know what they look like, we can use the tools. And what do we use with quadratics? We factor. So let's factor. We're going to factor upstairs. We're going to factor downstairs. So, upstairs. Well, what do we want? We want two numbers that when we multiply them together, we get positive 6. When we add, we get negative 5. So, it's not too hard to come up with two numbers that do that. Minus 2 and minus 3. So that would be e to the x minus 2, e to the x minus 3. Downstairs, similar. Two numbers that multiply to give negative 4, but add to give negative 3. And it's not too hard to come up with numbers that do that. I claim negative 4 and positive 1. Let's check. E to the x times e to the x, e to the x squared. Plus e to the x, subtract 4e to the x, minus 3e to the x. Nice! And then minus 4 plus 1, negative 4. It's like it was meant to be. Okay, and the same happens upstairs. Now, we're looking for divide by 0. So we start asking ourselves questions. Well, when can things be 0? So let's start with this e to the x plus 1. Okay, well, this would be 0 if e to the x plus 1 equals 0, or e to the x is negative 1. Well, can the exponential function be negative in our class? Now notice I added the in our class. Well, in our class, no, because we're trying to keep it real. But you might say things can get a little bit more complex. Well, that's a different class. So for us, e to the x can't be negative. We're not dividing by 0 because of the e to the x plus 1 term. Whew. Good. Now, that means that's not going to be a vertical asymptote to worry about. And it's good not to have vertical asymptotes. The fewer we have, the less work we have to do. Well, okay, what about this part? And I guess we should mark nothing happens here. Here, well, this would be e to the x minus 4 equals 0. E to the x equals 4. Can that happen? Well, yeah, it can. That would be x equals natural log 4. Okay, so the denominator can be 0 at log 4. Now, what happens to the numerator at log 4? Well, you'd have e to log 4, which is 4. So you have 4 minus 2, which is positive. 4 minus 3, which is positive. So you end up with a positive number divided by 0. Okay, things are blowing up. Great. All right. So, good. So when it comes to our vertical asymptotes, we have a vertical asymptote at x equals log 4. Now, are we done? Well, we're done with the first sentence, but then they kept going. And they said, well, we want you to go further. Namely, we want you to find some one-sided limits of f of x and on each vertical asymptote. So the good news is there's only one, so each means just the one. So we want to say, well, what's happening as we take the limit as x approaches 1 from below, not 1, log 4 from below, because we're at our asymptote, yeah, excuse me about that, of f of x. And what's the limit as x approaches log 4 from above of f of x? Okay, so we really have two more things we have to figure out. All right, well, let's think about it. Okay, so let's do these limits. And the nice thing is we don't really have to, it doesn't say justify, we just have to write down the answer. But I think to help us, we'll go ahead and say, well, let's work through the limits. So we'll start with the negative. All right, so we're going to do a limit. X approaches log 4 from below of e to the x minus 2, e to the x minus 3, over e to the x minus 4, e to the x plus 1. Now, what helps us figure out how it blows up? Well, we're really going to be looking for signs. So, we're near log 4. So, e to the log 4 is about 4. So 4 minus 2, this is about 2, positive number. 4 minus 3, this is about 1. 4 plus 1, this is about 5. Whoops, 4 plus 1 is 5. I know how to add. What about this part? Okay. Think of your exponential function. Here's log 4. Here's 4. We're coming from below. When we're coming from below, that means we're coming from the left. So we're coming from this direction. So I'm a little bit below log 4. What's my value? Well, e to the little bit below log 4 is a little bit below 4. So I have something below 4 subtract 4. So this is small negative number. All right, so the punchline is positive, 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 and a small negative. So we have the whole result is going to be huge because this is close to 0. The sign is negative, right? Plus, 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 minus. So what's the conclusion? Well, the conclusion is this is going to blow up towards minus infinity. The sign is coming from here. Okay, so minus infinity. On the other side, it would be a very similar argument. So, limit as x approaches log 4 from above. And again, e to the x minus 2, e to the x minus 3, e to the x minus 4, e to the x plus 1. Okay, again, go through it. This will be about 2, this will be about 1, this will be about 5. Here, what's going on? Well, what's going on is we're coming to log 4 from above. So when I come to log 4 from above, I'm a little bit bigger than 4. So e to the x minus 4, this is a small positive number. So positive, 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 but this is near 0, so it's blowing up. So the sign is to positive infinity. So that's the other one-sided limit. Whew! Oh my goodness, that one. I got to think a little bit on this one, but that's all right. So that's the idea. So vertical asymptote at x equals log 4. Look at the pieces of your function. Help you determine the sign just below and just above, right, on either side. And so you just have to think about particularly the part that's causing the 0, what's happening to that sign, and that'll help you determine what's going on. Number 6, we're asked to use the limit definition of derivative and compute the derivative of this function. F of x equals x divided by 2x plus 4 at the point x equals minus 1. All right, good. So we're a derivative at a point. Okay, well, great. So now we say, okay, what do we need? Well, we need to know the limit definition of derivative, and then we have to understand the tools. Now the tools tend to fall into a few simple categories. You have expanding, so in other words, quadratics multiplying out. You have dealing with square roots, which comes from multiplying by conjugates, dealing with fractions, which means adding fractions. Usually, once you can do those three things, these are pretty much self-working problems. All right, so we're going to go through and follow the steps. Now we're going to be really careful because, of course, we can't just take the derivative. We know how to take these derivatives with various rules. We have to follow what it says. If we don't use the limit definition, we're in trouble. So here we go. So what's the limit definition for f prime of 1? Sorry, f prime of minus 1. F prime of minus 1. Well, that's the limit as h goes to 0. I always prefer the h definition. It's the easiest to figure out what's going on. So it's f of minus 1 plus h. So wherever you're taking your derivative, plus h, subtract f of minus 1, that's your point you're taking derivative, all over our h. Normally, by the way, we write this as f prime of a is equal to the limit as h goes to 0, f of a plus h minus f of a over h. So what I've done from here to here is just plug in minus 1. Okay, well, that's the first step. Now, even if you just get this, points, because you know the limit definition. But we just don't know it. We know how to use it. So that's going to be where we get more points. Okay, equals the limit as h goes to 0. All right. Now, what comes next? Well, we plug things in. So our input is minus 1 plus h. So everywhere where we see an x, we put minus 1 plus h. So minus 1 plus h, divide by 2 times minus 1 plus h plus 4. Then minus 1, 2 times minus 1 plus 4. All that over h. Whew, okay. Well, what do we have? Let's clean this up and be careful here. Now, this all over h, let's go ahead and put this as a 1 over h in the front. So that 1 over h comes from here, that h. The first term, we have minus 1 plus h. Downstairs, well, notice we have a minus 2 plus 4, so we can write that as a 2, and 2 times h is 2h. Here we have minus 1, so that can be written as a plus 1, right? 2 minuses, 2 wrongs make a right. Minus 2 plus 4 is 2. Okay, so we've plugged in to the function. So this step, that's a lot of places where people make mistakes. And just sort of say, I'm not even going to think about it. Everywhere where I see x, I replace it by whatever I have here. I just do it. Similar, everywhere I see x, now I put minus 1. Just write it out. Okay, so here we say, we have fractions. How do you deal with fractions? You get common denominators. Now, on the first fraction, we could have said, hey, this first fraction is really 2 times 1 plus h, and then we have plus a half. Say, well, to get a common denominator, on that second part, you'd add a 1 plus h. And so that's what we're going to do. We're going to do exactly that. Okay, so that's a little bit of side work. So we'll make sure we keep that to the side. Limit as h goes to 0, 1 over h, and then we have negative 1 plus h plus 1 plus h, and over 2 plus 2h. Here we have 2 plus 2h. Okay, well, add. Since the denominators are the same, we can now add numerators. 1 over h, the negative 1 plus 1 cancels. Coincidence? No. Things should be getting simpler at some point. And if things aren't getting simple, mistakes were made. So this is a way you're like, oh wait, things didn't get simple. Backtrack and say, where's the mistake? Now, in particular, where are we going for? Heading towards, I should say. Well, we're heading towards the point where we can cancel some h's. And if you can't cancel h's, something has happened. All right, so if we've lived a good, clean algebra life, which I hope we have, you can cancel h's. So that's what I mean. If you cannot get to a point where the h's cancel, mistakes have been made. But now that you know mistakes were made, that helps you say, whoa, let me go back a few steps and let me find out where my mistakes are. It's good to know that, hey, I can catch myself. As the great mathematicians often say, you should check yourself before you wreck yourself. Okay, now, what comes next? Well, once you cancel h's, you say, oh, have I gotten rid of 0 over 0? Well, plug in h equals 0, and you get a number. Well, we do. What do we get? We get 2 over 2 plus 0, which leaves us with 1. So there's our answer, 1. And we're done, right? Because we used the limit definition. And we can even add a little note here that we said, hey, plug in h equals 0. We don't need to put this note, but that's what we did. Now, a few comments. When you're taking the limit definition, don't forget, you need to write the limits down until you actually take the limits. If you stop writing limits, you'll lose a point because, we really care about notation. Mathematicians are very like, give me notation or give me death. It's like, we want our notation. And so make sure you're careful about that. Make sure you're careful with your algebra. It's 90% algebra. Once you get past plugging in to the function, it's all algebra. So be careful, take your time. And one more thing we can do is, it's true we won't get any credit for taking derivative but another way, but we can do a sanity check. So what's a sanity check? Well, it says, look, I can take the derivative in a different way and I can check, do I get 1? So let's take our derivative. Here we'd use a quotient rule. So we take the bottom, 2x plus 4, times the derivative of the top, minus the top, times the derivative of the bottom, which is 2, all over the bottom term squared. Okay, now plug in -1. So f prime of -1, well, minus 2 plus 4 is 2. Subtract minus 1 times 2 is minus 2. Downstairs you get minus 2 plus 4, which is 2 squared. Well, 2 plus 2 is 4. 2 squared is 4. 4 over 4 is 1. So we say, yes, good, it matches. Now, what happens if your sanity check doesn't match? Go through your work in sort of both places, because these should match. The limit definition should match if you know how to take a derivative in a faster way. You don't have to do the sanity check, by the way. It's just a nice sort of like, I want to be extra careful, extra sure. But it's nice to know you have ways to check your answer. And this brings us to our final problem, number 7. And this problem concerns the following function. And what a function it is. We have x squared plus 4 below -2. At -2 we're 6. And then between -2 and 0 we're x squared plus 2x over x minus 6 times x squared. And then we're 1. And then we're sine 2x over tangent x cosine x if we're above 0. Okay, interesting choices we've made here. All right, and we have parts A, B, C, D. Oh, and we're told not to use l'hôpital. Well, we know what that will be later on in the class. But okay, for now, part A. Determine whether f of x is continuous, has a jump discontinuity, or a removable discontinuity at x equals -2. Okay, well, so what do we do? Well, what we're going to do is take a look and say, well, let's look what's happening around -2. And so we're going to look on both sides. So we're going to take a limit as x approaches -2 of x squared plus 4. And we're going to take a limit, and that's, sorry, from below, right? So below -2, we look like x squared plus 4. And we're going to take a limit as x approaches -2 from above of x squared plus 2x divided by x minus 6x squared. Okay, and let's compare. So the first thing is check these limits. And depending upon what the limits are, then we can go even further. So what do we have? Well, -2 squared plus 4, there's no problems. So we plug in. So this becomes -2 squared plus 4. 4 plus 4 is 8. Here, what do we have? We have -2 squared plus 2 times -2. Downstairs, we're going to have a -2 minus 6 times -2 squared. Now upstairs we get what? We get 4 minus 4, which is 0. Downstairs, -2 minus 24, which is not 0. Now, if this hadn't been 0, by the way, we couldn't just simply plug it in, but you should always check by plugging in. And if you get 0 over 0, more work, more work. But this is 0. Now, notice what's true. They don't match, but they are numbers. So essentially you have like a jump, right? Because on one side it says, oh, I think you're 0. And the side, oh, no, you should be 8. So what's going on? So when the one-sided limits exist but don't agree, it's a jump discontinuity. All right, so we can make a comment. One-sided limits exist, but do not match. And so we are jump discontinuity. We have to lift our pencil. It doesn't matter what the value is at -2. It doesn't matter that the value at -2 matches with neither of those. It doesn't matter. Once we know that the one-sided limits exist and don't match, we're done. Okay. On to part B. Determine whether f of x is continuous, has a jump discontinuity, or a removable discontinuity at x equals 0. All right, same game. So now we're going to say, well, what's going on at x equals 0? Okay, so limit as x goes to 0 from below. Now, that's below 0, right? See, notice here we're just below 0. So we're looking at this piece. We don't look at the 6 with x squared plus 4. Those are far from 0. The part just below 0. We have x squared plus 2x over x minus 6x squared. Now, let's pause and work this out really quickly. Notice you get 0 over 0 because all the terms have an x. But wait, all the terms have an x. So let's pull an x out and cancel. So I'm going to divide everything by x. And I'm allowed to do that because we're away from 0. So I don't need to worry about, oh, but wait, what about 0? Well, it doesn't happen. So upstairs we'd have what? Well, we would have x plus 2. Downstairs we'd get 1 minus 6x. Well, okay, now what do you do? Well, you plug in 0, right? You always say plug it in and see what happens. And if you get a number, life's great. And if you don't, more work. Well, plug in 0, we get 2 over 1. Well, that's great. So we know from below, our limit is 2. All right. Now, from above. Well, from above, what's happening? Limit as x approaches 0 from above. Well, we have now, we're this part. Sine of 2x over tangent of x cosine of x. Now, sine of 0 is 0. Tangent of 0 is 0. 0 over 0, more work. More work. Okay, so how do we do it? Well, we look to cancel. Now, one of our problems, and perhaps a hint at one of our solutions, is that the insides don't match. You see, we have a 2x here, but downstairs we have x's. But we can use that to our advantage. We could say, let's replace sine of 2x by something more friendly. Well, what's more friendly than sine of 2x? Well, the answer, and we're still a limit because we haven't finished taking the limit, is double angle formula. 2 sine of x cosine of x. And tangent of x, by the way, that's sine of x over cosine of x times cosine of x. And now we say, ooh, or maybe, or maybe, hey. The cosines downstairs cancel, sine cancels, and we say, oh, well, that makes it a much more palatable limit. So this is the limit as x approaches 0 from above of 2 cosine of x. Well, plug in 0. No problems, because we canceled some zeros. And we get 2 times cosine of 0, which is 2. All right, so what can we conclude? Well, at this point, we can conclude that when we come from both sides, they agree. So, putting these together, we conclude that the limit as x approaches 0 of f of x is 2, because both one-sided limits exist. However, what is f of 0? Plug in 0, what do we get? We get 1. So this does not equal 1, which is f of 0. So the limit exists, but it doesn't match what the behavior of the function is. So when the limit exists and it doesn't match the behavior of the function, then our conclusion is this is a removable discontinuity. In other words, you just have to plug in and say, look, change the value of 0. All right, on to part C. If the answer to A and or B was a removable discontinuity, how should the function be defined at the points to make it continuous? Well, A was not removable, so we don't need to worry. B was removable, and the problem was that it didn't match at 0. So we should say set at the function at 0, f of 0, should match the limit at 0, which is 2. That's it. We're done. Wow, we made it. We made it. What a fun exam. I hope you have fun practicing it, studying, getting ready for whatever it lies ahead. You can do this. You can do this. I believe in you. So keep it up. You'll be great.